Welcome back, everyone. And this is the continuation of section 11.1. This is part C of 11.1 sequences. We were seeing some examples of sequences and finding the limits and determining whether the sequence is convergent or divergent. So here we found in the earlier example, limit of n divided by n plus 1, then is a sequence. And also in that example, the conclusion is that the limit is equal to 1. But if you notice here in this particular example that we did before, if you look at this n over n plus 1, this was the very first example we gave regarding sequence. So this is, if you consider a sequence whose nth term is n over n plus 1, if it is this sequence, then we are finding the limit of the nth term of such a sequence. So here we don't have that curly bracket, but we are finding the nth term, and then the nth term approaches the limit 1. So what does it say about the sequence? This also tells us that the sequence n over n plus 1 is convergent. Though this is not the question is only asking us to find out the limit. So you can just leave there. But if it asks determine whether the sequence is convergent or divergent, then you can say that the sequence n over n plus 1. When you say sequence, you have to make sure that it is written inside a curly bracket. So that problem is telling some more information about that. Next, example 5 is the sequence an, which is n divided by square root of 10 plus n, convergent or divergent. So by definition, we know that limit is n approaching infinity. So what do we know in the definition of whether the sequence is convergent or divergent? If the limit of the nth term of an exists, then sequence an is convergent. So it pretty much we are going to decide by looking at the limit of the nth term an, which is limit as n approaching infinity of n divided by square root of 10 plus n. So whenever you have in n approaching infinity, anytime you have n approaching infinity, if you bring the terms to 1 over n to the power something, then you can use that limit as n approaching infinity of 1 over n to the power r equal to 0 because it's 1 over a large number. So always when you have a problem where n is approaching infinity, um, look for look by bringing the terms to the form 1 over n to the power of something. Okay? So here we are going to divide the numerator and the denominator by just n. So it is limit as n approaching infinity. Numerator is n divided by n1. Denominator, you have a radical, which is within the radical you have 10 plus n. Then you have outside, you are dividing that by n. You cannot divide a radical by a non-radical, so you have to make it look like a radical. So we'll write n as square root of n square, and this is possible because n is only positive. Otherwise, you have to write square root of n square as absolute n. But here n is allowed to approach infinity, so n is positive. So you are able to write n as square root of n square. Now it is possible to divide. That is limit as n approaching infinity, 1 divided by everything within the radical now, 10 divided by n square plus n divided by n square. So 10 divided by n square, a number divided by a very large number, that is 0, then this will be 1 divided by n, right? This will be 1 divided by n, which will be equal to 0 as n approaching infinity. as n approaching infinity. So this will be equal to 1 divided by square root of 0. Both terms are 0. It's 1 over 0, which is equal to infinity. So this tells us that because the limit of the nth term, because the limit of the nth term is infinity, we can say the sequence with the nth term n over square root of 10 plus n is divergent. Next, calculate limit is n approaching infinity, ln n over n. This is example 6. So normally when we do the limits from our calculus 1 class, we immediately plug and play. That will be our usual step. Step 1, so you do limit as n approaching infinity, ln n over n. So if you plug and play, then it is ln of infinity over infinity, so which is infinity over infinity, which is an indeterminate quotient. So anytime you have indeterminate quotient, you will apply L'Hopital rule. But L'Hopital rule is applied only to functions. So you cannot apply L'Hopital rule keeping n as an integer, because when you say ln n over n, it is an integer. N is an integer. So they are terms corresponding to, they are terms of a sequence. So a sub 1, a sub 2, all these are values corresponding to n equal to 1, n equal to 2, and so on. They are terms of a sequence. So you cannot apply limit L'Hopital rule to a sequence. So now we have to refer to the theorem that we did earlier, which is like this. If limit of a sequence equal to L, and if by changing x to n, if you get the nth term of the sequence, then limit of the sequence would also be L. So we apply this trick of relating function. So instead of doing the L'Hopital rule, for this sequence ln n over n, we are going to apply the same thing for a relating sequence. So we are going to consider a relating sequence, relating function. Relating function, which I call it the ln of x over x. See, notice that I'm changing the n here to x. So then we are going back to, then also what do you notice here? If I change the x to n, I get ln n over n, which is nothing but the nth term of the sequence. Right? So now let's apply the L'Hopital rule for this particular function. So let's apply limit x approaching infinity, ln x over x, so which is again infinity over infinity, which is indeterminate quotient. So apply L'Hopital rule. L'Hopital rule is limit as x approaching infinity of derivative of the numerator over derivative of the denominator. The limit as x approaching infinity. Derivative of the numerator is 1 over x. Derivative of the denominator is 1. So it is just limit as x approaching infinity of 1 over x, which is 0, because x is approaching infinity. 1 over a large number equal to 0. So this is about the function, but because we have f of n equal to ln n over n, so because of this, our conclusion here is that because the relating function is approaching the value 0, the sequence nth term is n approaching infinity, ln n over n will also approach 0. We use this trick in many problems, considering the relating function. Example 8, evaluate limit as n approaching infinity, negative 1 to the power n over n if it exists. So whenever you say negative 1 to the power n, we know that it changes the sign alternatively positive and negative. If I list down the members of this particular sequence, so what is this negative 1 to the power n over n? If I write down all the members, so it is going to be n equal to 1 if I substitute. It is negative 1 over 1. Then if I plug in n equal to 2, I get 1 over 2. Negative 1 square will be positive 1. Then it's negative 1/3, positive 1/4. So the terms are alternatively positive and negative. Whenever you have terms alternatively positive and negative, in order to find out the limit, we go back to one of the theorems that we quoted earlier. Um, so this theorem here, theorem number 6, if the limit is n approaching infinity of absolute a n equal to 0, then the limit of the nth term a n equal to 0. So that is the one we are going to use. So we are going to take the absolute value and then take the limit. So let's consider limit as n approaching infinity of absolute a n in this case. When I say a n, it is this part without the limit. So this is our a n. So that is limit as n approaching infinity of absolute negative 1 to the power n divided by n. Negative 1 to the power n divided by n. So what is the nature of negative 1 to the power n? It will be either negative 1 or positive 1. Negative 1 or positive 1 only. But when you take the absolute value of this, negative 1 to the power positive n, whether it is negative 1 or positive 1, the absolute value is after all 1. So limit is n approaching infinity, 1 on the numerator. But no matter what, n is going to be positive only because n is approaching infinity. So n is an integer also, it's only positive integers because it represents sequence of the terms of the sequence. The n approaching infinity, 1 over a large number, this is equal to 0. Because limit of the nth term, limit of the absolute an equal to 0, limit by that theorem, limit of an, which will also be 0. By the earlier theorem that we mentioned. What is the number that we quoted there? This is theorem 6, right? Theorem 6. If limit is n approaching infinity a n equal to L, and the function f is continuous, this is important, continuous at L, then limit is n approaching infinity of f of a n equal to f of L. But what this theorem tells us is that limit as n approaching infinity of f of a n equal to limit as n approaching infinity without the limit. The limit goes inside of f. So f, you take this limit inside the function, limit as n approaching infinity of a n, this will become f at, what is limit as n approaching infinity of a n? Given to be L, it is f at L. So for that, the required condition is that f should be continuous at L. So using this, we can do this example. Find limit as n approaching infinity of sine of pi over n. So we know that sine is a continuous function So we are going to take this limit inside the argument of sine. So limit as n approaching infinity, sine of pi over n is sine of limit n approaching infinity of pi over n. That is sine pi over n. Pi is a constant. N is approaching infinity. So constant divided by infinity, because you have a very large number, you are dividing a constant by a very large number, this has to be 0. But what is sine 0 equal to?